Okay, so let's see your prelim 2 graded exams are here. Please pick them up, and if you haven't picked up your solutions to the prelim, they're also there. And any of the old materials, please pick them up if you haven't yet. The thing is also, if you have any concerns or questions about the way the prelim was graded, if I missed anything, please let me know. I'll take care of it. And so the average this time was about roughly 16.7 out of 30. And I think question 2 is where I noticed either there was some conceptual problem or it was not very clear what the question was, because I could see that you knew roughly what to do, but maybe the question was not very clear. So I noticed that, and that means that in the course of this class, I'll try to emphasize those topics, because though they were kind of covered, maybe they were not emphasized enough. So, yep, there was a question.
What was the average for the first one?
Sorry?
For the first one, where was the average?
The first 20 out of 25. Right. Okay. So she remembers. Yeah. And just so it's not like nobody got it. Quite a few of you got the questions as well, and all that. So yeah.
Do you have any idea what the standard deviation is?
Standard deviation this time was about 5. Yeah, 5 out of this much. So the other thing I wanted to say was, if you have been turning in your homeworks and have been putting in the effort, one prelim shouldn't affect things too much, but you do have the rough grades and the the weightages and all that in the class website. They're all distributed. Yep.
According to the weightage, like this prelim had more weightage than the previous.
Yes. So previous first prelim has 25%. Oh no, something like that. 15%. So yeah, this one had a slight more weightage, and the finals will have slightly more than this prelim. So okay, so the second thing I wanted to mention was, so we'll have office hours this week so tomorrow and Wednesday, and I'm able to do this, and let me know if this works. PM both days, 5 to 7 p.m. And I know you have your assignment due on Wednesday, but I got a few requests for extension. And I mean, if you have been working hard, you probably wouldn't like this extension, but let's make it Friday, this Friday. That's the 9th, right? So current assignment is due on November 9th. I'll send out an email instead of November 7th. Okay.
Sorry, Friday's 11th. Friday's 11th.
11th. Okay, so 11th. For assignment 5, right? Okay. And we'll have tomorrow and day after 5 to 7 p.m. Office hours for this week. Okay, so that, and the last thing I wanted to say was, starting the next assignment, in assignment 6, there will be at least one problem which will be kind of it will be a little bit of a lab work, meaning you have to go in and measure something about a laser in the lab. And it will be one of the questions, or maybe 2 in assignment 6. In assignment 7, you will actually make a full-blown laser and you will mode lock it. That will be part of assignment 7. So we are putting those things together, and I'll arrange, let you know. And what we will have to do for the last 2 assignments for these 2 problems, which is, one of the problems in the assignment is to go build or make something in the lab, and this will involve forming groups, because we can't have individuals. It'll take too much time. So I'm going to drop an email saying a group of this many people, probably it will be 4 or 5 people, a group will form a group, and then you distribute the job amongst yourself, and you go in and do the lab, make the laser or measure something about a laser in the lab. So the last 2 assignments will have that. So, yeah. Okay.
Are the office hours?
This week?
Yeah. Where are they?
Oh, yeah, sorry. This is in my office in Phillips Hall, 428B. That's where. Phillips Hall, 428B. Okay. Let's see. So what I wanted to do today was finish up a few things that we had left over from the discussion of various kinds of lasers, and then get started on semiconductor lasers. And so the last couple of things I wanted to discuss about various kinds of lasers. One of them is called the Excimer laser. I think let me switch this part off. Okay. All right. So we are discussing types of lasers, and we've discussed quite a few. Now, the one I wanted to, 2 of them I wanted to discuss today and finish up this survey of various kinds of lasers. And the first is Excimer. And the Excimer laser is something that's based on the rare or the noble gases like argon, krypton, and such things. I think, let me see this periodic table. Yeah, we can see this column here. And let's choose as an example argon. And argon we understand from classical or our knowledge from quantum mechanics in chemistry or in physics. It's very inactive. It's very inert, and the reason for that is it has all its orbitals, electron orbitals, completely filled, and there is no need. It's not missing one, or it doesn't have an extra in any orbital. It is all complete. For example, if you have 1s orbital, 2s orbital, 2 p orbitals, there are 3 of them, maybe px, py, pz, and all of them, each one of them can hold 2 electrons, so you kind of start filling, and maybe you fill up one s orbital, 2s orbital, 2p, and then you are out of electrons, so that would be a noble gas, right, or an inert gas, and then so on. And it repeats periodically, hence periodic table and all that, right? So if you have that, and if we look at argon, for example, indeed it is inert, or it's chemically very unreactive. But if you do something to it and you pull that electron, outermost electron, let's say, not necessarily in 2p orbital, but wherever it is, you pull that outermost electron out to a higher orbital, or you excite it, that outermost electron, then the argon, essentially, you can look in the periodic table, it will start looking a little bit, or you kind of inject an extra electron to it, whichever way, I don't know. You have obviously many higher orbitals that are unoccupied, and you inject an electron into it. It's charged now, but electronically the argon starts looking like the next element in the periodic table, which is potassium, for example. It has an extra electron now in the orbital. It's obviously very unstable, doesn't like it there, it would like to decay, right? But if you can inject it there, it's an unstable situation, but electronically it looks like potassium, but its nucleus doesn't, it has one less proton, so it doesn't like it, it's charged, right? So that's the picture. If you take argon and you excite it, or you maybe pull out one of the electrons, or do something to it, you excite it, you create an element that looks like the next element in the periodic table, and that's the next element in the periodic table after the inert gases are extremely reactive. These are potassium, sodium, they have an extra electron, right? So they're extremely reactive, and they react very strongly with halogens, like sodium chloride or sodium fluoride or any one of them. They react very strongly with the halogens. And so, for example, an excited argon will react very strongly with fluorine, and it will form a chemical reaction, for example, right? So but you have to give it that extra energy to go over that hump of stability, you know? And this is the reason for the name. These are basically excited inert elements, which is the name excimer comes from there. You know, it's excited state. And I will just qualitatively mention this without going into too much details. For example, if I take argon and fluorine, a mixture of them, and then I shoot a lot of high energy electrons by injecting a large current into it, so I can knock out one of the electrons from the argon and ionize it. You know, so it becomes argon plus fluorine is neutral plus electron, which is negative in charge. And the amount of energy, so if argon and fluorine were sitting, you know, in steady state, then their energy would be somewhere like this, meaning if I take argon and fluorine and they are very far apart, they are very stable, their energy is 0. If I try to bring them very close to each other, then they repel because of Pauli exclusion and all that sort of thing, so the energy cost goes up. Pauli exclusion, Coulomb interaction, all that sort of thing. So this is neutral argon plus fluorine, whereas if you charge it up, the amount of energy you need to give the argon atom to pull out that electron is its ionization potential. It's about 15.7 electron volts. That's how much energy you need to give to this combined thing to just knock out an electron from argon. 15.7 eV. But when they are now apart and that electron is floating around, you can imagine now that the fluorine is extremely electronegative. It is missing an electron in its orbits, right? So it immediately tries to capture it, right? And it tries to capture it, and by capturing it, it will immediately lower its energy by its electron affinity, which is whatever it is, about 3 electron volt, 3.4 eV. It's going to lower its energy. So the combination now has argon plus and fluorine minus. Does that make sense? That electron that you knocked out of argon got absorbed by the fluorine, and it lowered its energy. And now they're charged, so they're going to attract each other, right? And as they attract each other, it's going to Coulomb lower its energy because of Coulomb attraction, and it will kind of reach a minimum here. And it will stay there for a few nanoseconds at this minimum energy. So stay there for a few nanoseconds before it realizes that, well, there is obviously a much lower energy state I would rather be in, and it relaxes there by emitting a photon now, light. So now you see you got kind of a roughly 4-level system. You kind of kick it up here, you relax, relax. So it's a 4-level system, and this is where the emission occurs of the photon. So this is the excimer laser. And so not the laser, this is the excimer emission, and then you put it inside mirrors and, you know, cavities, and then this is your gain medium then with a 4-level sort of thing, roughly. Right? And the physics of this is slightly different from the others, but and one can calculate the amount of energy you need to generate it. For example, in our lab in Duffield Hall, we are trying to make UV lasers, and therefore we need very short wavelength or large energy photons. And we use excimer lasers at 193 nanometer emission, which is about close to 6 electron volts of photon energy, 6 eV, 157. So you can kind of see if you choose, you know, argon and fluorine, you expect about 193 nanometer emission. You choose krypton and fluorine. I mean, these are the possibilities. So you have your rare gases, so the inert gases, and you have your you know, group 1 elements, halogens, the fluorine, chlorine, and all that. Yeah, there's a question.
How energetic can you go? Can you go further than ultraviolet and go X-ray or gamma ray laser?
That's a good point. So it really depends. You see, the most ionization potentials of atoms are about kind of less than 20 eV, mostly, right, from the outermost shells. Right, so if you kick out the outermost shell electrons, so that's where you're limited. So the very short wavelength UV, but not too far then. Gamma would be very high energy. Right. So for gamma ray radiation, because the deepest electrons in heavy elements are in kilo electron volts or some keV, thousands of electron volts. That's still not enough for kind of gamma rays. You know, gamma ray typically you need the strong or the nuclear forces to kick in for gamma rays, for radiation. Also, X-ray you can. X-rays you can. So you can get it, but you have to pull out electrons that are very deep down in the core electrons, not in the outermost shells. Then you could get some radiation in the much shorter wavelength than this. This is the Excimers are typically very nice for UV and that sort of thing. It's used for laser eye surgery to cut, precisely the muscles of the, the lens of the eye. Excimers are used for the laser eye surgery. So, okay, so and you can get nice amounts of power in the UV using this the Excimer lasers. And the last one, again, this is a survey. I'm not going into too much detail, but hopefully give you the rough flavor of it. The last one is something that is somewhat new. We haven't really discussed the physics of this particular laser, which is the free electron laser. Free electron laser is almost a classical laser, meaning you don't need to know any quantum mechanics for this. There's no spontaneous stimulated ideas here. It's all classical, meaning you, if you know classical electromagnetics and a bit of relativity, which is considered classical mechanics, this is how you make a laser using classical physics, and it basically gives you enormous amounts of power over a very wide window from microwave to UV. Enormous amounts of power, except basically you need a big building to hold this. It's a huge facility, and there are quite a few around. These are user facilities. The idea is actually okay. So I'll just write that down. Free electron lasers. And again, this is in the spirit of the survey for this course. So one of the first things people realize that if you have electrons, whether be it electrons in a metal wire or free electrons in a vacuum tube, whichever way, if you take that electron and you basically physically oscillate in real space, if you kind of move it back and forth, if you kind of oscillate it with a frequency of omega naught, let's say, omega naught, then it's going to radiate. It's going to radiate out electromagnetic radiation or electric and magnetic fields. This is what's called a dipole antenna. You take an electron charge and you basically slosh it back and forth, like what happens every time you make a call on your cell phone. That little metal casing is the antenna, and the electrons are sloshing back and forth at 4 gigahertz, so you get your 4G signal, for example, right? So electrons go back and forth and they radiate, and when they radiate out, this radiation is roughly, at this frequency at which it's oscillating, and when you radiate it out, you have an electric field and a magnetic field, and essentially, that kind of electric and magnetic. So you get an electromagnetic wave that goes out. It releases this electromagnetic wave is it's detached from the electron and it's free to move in space now. So that's the idea. And if you have taken EMAG courses or something, you would see exactly how what is the MAD. This is called the far field pattern. There's a certain amount of energy that stays stuck to the electron called the reactive energy, and then the near field that kind of breathes out and in every time it oscillates, and a part of it which escapes, and that's the radiation, right? And so classically this was understood and by J.J. Thomson and others who discovered the electron, and people who discovered the electron, they had formulas for all that, and they could find out the radiation pattern, and the radiation goes perpendicular to the direction of oscillation. It doesn't go this way or that way. Now you can play games, you can combine them, few antennas, and you can direct it, make it go this way or that way by combining various radiation, then you form an antenna and all that sort of thing. So that's directed energy. And I think you understand that laser is extremely directed, right? It's extremely directed, whereas here the energy is kind of going out quite a bit here, a little less here, little less here, little less, and nothing here. So that's it. So we want all of it almost to go in that direction, let's say in a laser. So what you do is actually in a free electron laser, the basic energy emission is using the radiation, electromagnetic radiation from an accelerating charge, but then you basically start moving this electron at an extremely high speed at the same time. And when you start moving at extremely high speed, how high? So V along the z direction, let's say, is roughly 0.999 times speed of light. That's how fast you actually start moving it in a certain direction. So what you do is you create a vacuum tube, which is typically tens of meters long, and you evacuate, and you have an electron beam going into it, and you have very high voltage that accelerates it and reaches this sort of a velocity. It's very high speed. It's relativistic now. So when it moves that fast, what happens? This radiation pattern, instead of being symmetric like that, it basically becomes very directed on one side and a little bit on the other. So when it starts moving like that, and that's shown here, it's moving very fast relativistically, and the radiation pattern starts looking. It's not completely a laser, but it's like that. The beam becomes very directional. Yeah, there's a question.
So do Einstein's equations work for this?
Absolutely. I mean, you need that in the first line to get next step to design it. Basically, I think that the V square or C square and all that, so that will be your the momentum and all that. So these are what are necessary to analyze this the free electron laser. But the main idea I wanted to get to is how is it that you are getting energy out of this, because you're accelerating electrons. If you think of it classically, if I do the same thing in a a metal wire, I'm going to lose energy by radiative losses and all that sort of thing. But now you're in vacuum, so it has nothing to collide with, A. And if I am flowing a current in this direction, let's call it a current density J. I think it says, okay, J is a current density. It's in amps per centimeter square. Current per unit area with a certain direction in which it's going. Let's say it's J naught times Z. It's going in the Z direction. So the amount of and the idea now is it's radiating an electromagnetic wave which has its wavelength. The electromagnetic wave has a certain wavelength lambda naught, and so if it's going in that direction, the electromagnetic wave that's radiated actually has its electric field. If it's going in the Z direction, the electromagnetic wave radiates in the transverse direction. E and H, it radiates in the transverse direction. And from here, if you want to say how much output power am I going to get out of this, where an electron wave is going through and there's electromagnetic wave that's interacting with it. So there's electric field that's oscillating very fast in space and in time. In time, it's in hundreds of terahertz. That's the frequency of light waves. And in space, depending on the wave, if it's UV, it's hundreds of nanometers. If it's visible, it's about a micron, or half a micron, and so on. But P out, the output, is I times V. That's the output of a current and a voltage. And we can write it slightly differently here. Let me write it in this way: J dot electric field and dt. That's energy out. So J dot E is the output power integrated over time will be the output energy. This again qualitatively, I'm not going to go too deep into it. Just point out how does this work. So the electric field is the optical wave electric field, meaning of the electromagnetic wave radiation. So the current is going of electrons, and it's interacting with a light wave that has been already generated, and it's interacting with it, and then the output power could be negative. I mean, basically it could be negative, it could be zero. Typically, if you are flowing such a current in a wire, it's lossy, it's negative. So you meaning you dissipate power. You have I square R sort of loss. Here, what I'm saying is you can actually have gain, and the way you assure that is you do two things. First thing, you note that if you look at the current, it's going in the Z direction, whereas the electric field of the electromagnetic wave is perpendicular to it, and therefore the dot product is going to be zero. Z dot optical field is in the transverse direction, is going that way. So that's 0. So that's a problem. That means there's not much interaction. I can't have gain. And the second thing is, if optical electric field, it's always an amplitude times some cosine, omega naught t, and then it's pointing in the transverse direction. And if the current is uniform, and you integrate it over any number of periods, you'll get a 0. Cosine omega t or sine omega t, you'll get a 0, right? So you get kind of 0 interaction by two ways. One is the direction of velocity of the electron or the current is perpendicular to the electric field. Therefore, dot product is 0. Second is the electric field of the light wave integrated over any cycle is 0. If this is constant, then the integral will be 0. There's no interaction whatsoever. So you can't make a laser if you just go with this. So you kind of tweak the design slightly. And what you do is, instead of the electron going along the z direction completely, you make it kind of go like this, and you physically, in real space, you have a wiggler. These are wigglers called magnets. So you have physical magnets, and the electron comes in, and because of the Lorentz force, E, electric field, and velocity cross magnetic field, it tries to do a circle around a magnet, right? And then you have the opposite magnet, opposite, and then it kind of goes through a real space wave-like motion. So as the electron, remember the speed along the z direction is very fast. It's speed of light almost, whereas in lateral direction it's just slight wiggles, not very large, but slightly. And the velocity in the vertical direction is very small. And from that, the moment you do that, what you give it is, let's say the velocity here is in this direction. You have a v along the z direction, but now you also have a transverse velocity, right? Just because of this wiggler. And therefore you break this deadlock here. It says, okay, I have a little transverse velocity now, a, right? And the second thing you do is you choose this frequency, and it has a characteristic wavelength once you know the frequency, wavelength of light. And the wigglers are separated, because this is kind of the wavelength of the real space motion of the electron. And the wavelength here should be such that, if my velocity is, let's say the velocity in the transverse direction is this way, and the electric field that's oscillating, again qualitatively here, has a positive sign here, then at this point, let's see, it's oscillating very fast. The wavelength of the light wave is much shorter. I'm not drawing the right picture. The wavelength is much shorter, but if the velocity in the transverse direction is this way here, after half a period, it's this way, right, of the electron. And then the electric field of the light wave, if it's this way here, it should be also in this way, such that it always adds. Every time you go through and interact, you get a j dot E, which is the same sign, so that it builds up. Every cycle it adds up. If you don't have this, if you have it go back here, then this, the j, or the velocity of the electron, has one sign here, the opposite sign here, it will cancel out. Every period it will go to 0 again, right? So you do this design, which gives you a very simple kind of criteria that the distance between the wiggler, the magnets that do the wiggling, should be of the order of the velocity in the z direction over speed of light minus velocity, roughly. So this is kind of a rough order of magnitude. And if you plot those things in, if this is a micron, this will be in centimeters or sometimes 50 centimeters. So these are physically really separated distances, because if the velocity along z direction is very close to speed of light, you get this factor is very large, and therefore you get the wiggler separation is pretty large. So that's a very qualitative explanation, but if you want to go further into the quantitative aspects of how much power is coming out, what is the exact distance between the magnets and all that, you can do the calculations of that. And then actually I must say that the calculation is not that involved, except you have to solve the relativistic equations. For example, rate of change of momentum is equal to the Lorentz force, electric field plus V cross B, but the momentum has this gamma, which is the Lorentz So gamma is 1 over square root 1 minus v square over c square. You have to just kind of take care of that aspect of it. So then you get this coupled equations one needs to solve. In your book, they have made a meek effort of doing that, but you see it's a coupled equation, velocity and velocity kind of get tied up, and gamma has a velocity in the denominator, so it gets a little tied up. So, but you can solve it. So that's the rough idea. The main thing here is if you take a stream of electrons and you let it just go straight through, in one direction, and it's radiating charge, it's still going to be lost. It's not going to be able to generate any energy. But if you kind of swirl the electrons around and make it kind of synchronize with the wavelength of light in the right way, you can get gain out of it. In fact, this is the concept also of the first vacuum tube amplifiers. Before transistors came along, the vacuum tubes used to have an electron beam go through, and they, basically physically instead of wigglers in a vacuum tube, you have the electrons were kind of made to swirl. The motion was almost cycloidal, so that it gets synchronous, and it gets, when the velocity is this way with electric field here, and velocity is this way with the electric field of light wave here, it can kind of generate power rather than losing it. So you can actually do that. So it came from vacuum tube sort of ideas as well. So in fact, even today, the highest efficiency, the largest amounts of power you can get for amplification at high frequencies for electronics uses vacuum tubes. Transistors still don't cut it at very high frequencies. Meaning, if you want at 1 terahertz frequency, you want watts of output power. These are called klystrons and all that. These are real vacuum tubes, sort of devices that transistors still can't match today. So yeah. Okay, so that's it. It's a quick discussion. But if there are any quick questions, I'd like to answer. Yeah.
So, what are some typical numbers of V sub C? Like, are they like magnitudes different from C or
V sub Z?
Yeah.
So that would be, as I was mentioning a little earlier, it's almost 99% of speed of light, let's say. So it's close to 2.98 times 10 to the power 8 meters per second. It's very close to speed of light, almost close to speed of light. So it's radiating now, right? A lot of energy is being radiated out.
So
and yeah.
When you say that distance between the magnets is like quite large.
Yes. Yeah. So what I was trying to say here is, if I kind of require this criteria that if I have because of the magnets and the wigglers, we have velocity of the electron that's going this way, and if I require that it be such that if I'm at a maxima of electric field positive sign here, I'm at a minima and negative sign here, I get that relation right away, that this separation of the magnets should be equal to the wavelength of light that is being radiated times this ratio of velocities. And this number is a very large number. And you can kind of, because you see, it's basically kind of 1 over a very, like a 0.0001 or something like that. So it's kind of 1,000 times or something like that. So yeah. Okay, you can read a little more about it if you're interested. And then these are, as I mentioned earlier, these are sources of huge amounts of power. And it may not be extremely coherent, and the coherence lengths may be low, but power density is extremely huge. And generally these are large facilities, not a tabletop equipment. Okay, good. So I think we are done now with the discussion of various kinds of lasers, except the semiconductor laser. So we talked quite a bit about gas lasers, tunable, Excimers, free electron. But let's get started on the semiconductor lasers. Okay, so before I get started with semiconductor lasers, let me just kind of briefly give a kind of a broader perspective of why are semiconductor lasers, why have they become absolutely extremely important in modern day communications and data transfer and many other applications. In fact, as you know, there's a very big industry built around it, and the optical fiber communications, very fast, high-speed data transfer make use of these lasers. And the concept of the semiconductor laser is exactly the same as all the earlier lasers except the free electron. All the other lasers we have talked about, it has a certain gain coefficient, there's a cavity, and it radiates a certain, when gain overcomes loss, it radiates a large amount of coherent light at a very specific wavelength. Now, but if you look at let's actually do a very rough numbers on the semiconductor laser first. A semiconductor laser, this is a typical design. Most semiconductor lasers will look like this. It's a chunk of material, and these are not centimeters, these are microns. 10 microns this way, 250 microns this way, and you have a PN diode of a semiconductor material, gallium arsenide or something like that. We'll go into all the details of which materials, why do you choose it, how, but let's just look at a broader perspective of why is it that it's so interesting and why is it has become so useful. So and so you have typically a PN junction, which is a diode, and therefore semiconductor lasers, typically the family would be called a diode laser, and a diode laser is not considered to be a solid state laser. This is a bit of a misnomer in names. A solid state laser, typically when you say solid state devices, we mean transistors and diodes and all that, but we don't quite mean, when we say solid state laser, that is reserved for things like ruby laser, where your gain medium is indeed a sapphire crystal and it's a solid instead of a gas. So semiconductor lasers are referred to as diode lasers because ruby laser is not a diode at all. So it's a PN diode, and we'll describe in great detail what we mean by all that detail. But here, the device, this is the entire device. So if you have 10 microns of a semiconductor material and 250 microns the other way, you can make your whole laser using just this tiny speck of material which you can't even see with your eyes. And then when you apply a few volts across it, we'll see now that it will output power. The output power is of the order of or even larger than the meter-long tabletop lasers that you have. So it is extremely efficient, and it has all these other very interesting capabilities that I'll point out today. Okay. So, all right, so let's just start by doing a very rough order of magnitude calculation based on all the knowledge we have developed till now. I want to know how much power is going to come out of this laser, A. B is what would be the gain coefficients of it for it to make it laze. And if we do a very rough calculation, we'll get a very quick feel for what a semiconductor laser is all about. So let's just do that. So what we are saying is we have a PN junction, and remember a semiconductor crystal is at least today it is the most perfect crystal ever created by human beings. The atoms are arranged in an absolute perfect crystallinity. Any break from there is going to cause losses in the material. So it's almost meaning if you have a 4-inch wafer, the whole thing is one molecule. I mean, everything is ordered, absolutely ordered. So which is the reason why it can provide you just enormous amounts of gain and all that. So we're going to see how that happens. So on top of this PN junction, so I've taken a semiconductor as an example. I've taken gallium arsenide, let's say. This is an example of a semiconductor. And in the P side, what I've done is I've replaced gallium, which is group 3 element, with some, with a group 2 element, which has one less electron. So it makes this region electron poor. This is, let's say, also gallium arsenide, but I've replaced gallium with something which has one extra electron, like silicon. So this is a donor. It donates. This region is electron rich. This region is electron poor. And it doesn't matter exactly, maybe beryllium or something like that. It doesn't matter exactly what I have substituted. Some gallium atoms, not all. And so that, as a result, you have a lot of empty states here that are supposed to be filled with electrons. We have a lot of extra electrons here. And what we do is we put down a metal contact on this, okay, on top. So I have a metal contact which connects to the whole swarm of holes or the missing electrons here. So it forms what you call as a p-type ohmic contact to this region. Similarly, on the back side, maybe you can sketch it. Okay, on the back side there will be another which connects to the extra electrons, swarm of electrons on the back side. And then we apply a voltage across it, and we forward bias this, meaning this battery tries to, there's a positive voltage here, so it tries to move positive charges that way and negative charges that way. And what happens is within this region now, when you flow a current, these extra electrons in a semiconductor, and these details we'll cover in the next class. Okay, today just a quick overview. So we have a band gap, and just like we had, your lower state E1 and E2 in an atomic laser, and you had population inversion and all that. Here we have bands of energies. So we have bands of energies. These are the manifolds in some sense of continuous states of energies. We'll see they'll lead to density of states and all that. But what's really happening is in this junction region, when I inject carriers, so inject holes, and the current will kind of spread out a little bit if I have, instead of just contact like that. Let's say I have a contact entire on the whole backside, let's say. So the current will flow like this, okay? And it will maybe spread out a little bit. All that. But as you flow current, you are injecting holes or empty states into this region. These are empty states. And you are injecting electrons from the n side into that region. So these are filled states. And you create a situation where they can recombine and emit photons. So that's the idea of the semiconductor lasers. So N and P, you inject electrons and holes, and they recombine at a junction region. And in that region, we'll see you can create population inversion under certain voltages and certain current injection. That's the, so we'll have to first discuss what population of what, and for that we'll have to discuss what are the density of states and all that sort of thing here. But before we go into all that detail, let's do a very rough calculation of, for example, what is the gain coefficient I need to make this thing to laze. So here are rough dimensions. I think you have 10 microns here, and you have 250 microns here. So this is a quarter of a was that a centimeter or something like that? I mean, yes, it's a quarter of a millimeter, so it's about that size. And when I'm injecting current, the current is kind of flowing through this little window here into the other side, and so what we're going to say now is I have created some photons here, and I've created photons here. The photon is trying to get out. Photon always moves with the speed of light, right, or c over n inside any material. So it tries to get out. So I'm going to build mirrors by cleaving this edge. What I do is, a semiconductor is a crystal, so when you cleave it, you get an atomically flat surface here. It's a crystal, atomically flat surface. And then you have a refractive index mismatch of n, which is roughly, roughly 3 order of magnitude. Refractive index of a semiconductor material is 3. Outside is air is 1, right? So you get a mismatch in refractive index. As a result, you get a, when the photon tries to get out, it's going to have a certain reflectivity. It's going to get back, turn back in, get out on this side, turn back in, and here's your cavity. So just cleaved faces on two sides. Now, one of the things is when you cleave it, when you take a semiconductor and you just cleave it, your reflectivity is of the order of 30%, roughly, give or take. Depends on the material. But it's like, n minus 1 over n plus 1 square and all that stuff. I think you know what is the reflectivity, right? So it's of the order of 30%, not very high. You can do other business, like you can put dBRs by depositing superlattices or ALD layers and all that. But if you don't do anything, it's about 30%. So now if I tell you that's 30%, then I should be able to answer now what is the gain coefficient I need to make it laze now. I should be able to say that now. How do I do that? Based on everything we have done till now in this course, so what is the gain coefficient in this active region to make it laze? How do I find that? So, yeah.
1 over the stencil length times natural log of 1 over the
Right.
square.
Exactly right. So, and the way you get to that point is you say that, well, I'm going to track a photon again, right? And see, it goes here, reflects R1, goes here, reflects R2, comes back here, and if there's any gain inside, So I have reflection R1, R2, and if I have any gain inside, I will have an amplification of e to the power gamma times whatever is the length of that cavity, right? Length of the gain medium. But I have two, I'm traversing it twice here. It's not a ring laser, so I'm traversing it twice. So that should be, 1, right? And if I have any losses inside the material, and then I'm just trying to emphasize it now, if I have any losses inside the material, then I should take away the losses too. So if I have some defects and other things that are kind of sucking away a part of the photons as they're going back and forth, I should take that out too. So that's the internal loss, not the mirror loss. It's internal loss. So that's the condition. And from here you get right away that gamma minus alpha, which is the net gain, should be 1 over 2 times the gain length, natural log of 1 over R1, R2. And my hope is in this course, if, as an engineer, this is the result you want to remember every time. Because the moment you know the reflectivities, you should be able to, I need this much gain. Without it, we're not in business for a laser. Right? This is the gain I need, right? And so if you put in the numbers here, let's say both are 0.3, right? 0.3, so you get what? Natural log of 0.09, so like 100 over 9, right? So let's assume that's natural log of 10. Natural log of 10 is like 2.3 or something like that, right? Right, and so the gain medium length here, remember this is the gain medium length, this is the longitudinal direction in which the photons go back and forth. It's about, we are saying it's about 250 microns for this case. So, so the gain, well, let's see, it should be greater than or equal to 1 over 2 times 0.025 centimeters. I want it in inverse centimeters, okay? Times 2.3, natural log of all that stuff, right? So what do I get? It's just, I get like a 0.05. So that's 20 times 2. So I get that my net gain should be greater than or equal to like roughly 50. 50 inverse centimeter for this case. So that's huge. If you remember all the gains you have calculated earlier, we're talking typically about a 0.1 inverse centimeter, 1 inverse centimeter. This is 50, and you can get 100 or few hundred inverse centimeter in semiconductors, and a semiconductor can provide you this much gain. It can provide you, and we're going to basically make the connection as to why and how does it do it and all that sort of thing. Okay, so now the second thing we want to see here is how much power will come out. Let's say so again. The losses in semiconductors will be, again, a few inverse centimeters, but the gain, we want it to be very high. And as your material, typically when semiconductor materials are being developed, you start with mostly loss, very little gain, and then as you make the material cleaner, better, less defects, this overcomes this loss, and then you get gain. And when you get gain, it's a lot. You can get a lot of gain. It kind of can track it down to the fact that you have such a dense set of atoms in a crystal, and pretty much a very large fraction of them are providing you gain instead of a very rare gas where the atoms are separated very far apart and all that sort of thing. Kind of very rough idea of why. The second thing we can do is say how much power is this going to deliver, right? So if the band gap of the semiconductor, if its gallium arsenide is about 1.4 electron volt band gap, and when we apply a voltage, we'll see later we'll have to apply slightly more than the band gap to make it emit. It will first start out as a LED, and then the moment, so it will first spontaneously emit. So the output power, let me just maybe plot it versus current, P out. Output power of a semiconductor laser diode will look like this. It will start out very slow, and then suddenly it will hit the lasing threshold, current threshold. So till then you'll be spontaneously emitting. So it'll be like a LED. It's just going to spontaneously emit. Then you reach the criteria for lasing, population inversion, and it will start emitting as a
This is like very mode locked, right? Because it's so tiny.
You said, is it mode locked?
Yeah, because the FSR is like massive, right? So
Oh, well, good point. Its bandwidth is huge, but I will discuss this later. You can very easily mode lock it. But to mode lock it, you will have to put a saturable absorber in series. So the way you do that is kind of etch down and put another one of these regions on the side as a saturable absorber. So the light goes out, absorbs a little bit, comes back, and so by itself it's not mode locked. You have to do something to mode lock it. But the gain bandwidth is large, and we'll discuss that in detail. By itself it's not. But I want to just finish by saying that here, if you calculate how much energy is going to come out of this, typically for such a diode, we will be injecting about 100 milliamp of current, typically. You see that, and then it's easy to calculate with PN diodes and all. We'll be injecting about 100 milliamps of current here. And the voltage we'll apply out here in the battery is, slightly more than the band gap, maybe 2 volts. Band gap is 1.4 eV. So we'll apply 2 volts. So the input power is 2 volts times 100 milliamps, roughly. And that's about 200 milliwatts. Yeah, that's how much power we are going to inject from the battery. And if we design things right in the semiconductor laser, if I do some nice business, I put quantum wells inside here. This is called a double heterostructure laser. And each of these ideas I'll introduce in the next class is kind of deservedly has won Nobel Prizes and all that. So it's kind of very nice. If I introduce some quantum wells, it's called a double heterostructure laser. I can make the efficiency close to 50% or 60%, 50 to 60% efficient, these things. So if I inject 200 milliwatts, I think you can easily say that output power will be 100 milliwatts from this little laser that you can't even see. It's so small, and it's outputting power that's kind of almost bigger than these big tabletop gas lasers, right? So this is kind of almost mind-boggling, but it's amazing that it happens, and the semiconductor material makes it happen. And we'll see in the next class that all the other tricks that, for example, in this laser, you can take this and you can apply, instead of a steady state voltage, you can apply an AC voltage on it. You can modulate it directly, right? You can't do that with a big laser because you're applying kilovolts on it. It's very hard to modulate it at gigahertz frequencies, very high speed. This you can turn it on and off very, very fast, which is why it is used for communications. You feed in photons on and off into the optical fiber, and that's how it makes it happen, because your volume is so small, capacitance are so small. And finally, because you're only applying a few volts and a few hundreds of milliamps, you can have a handheld laser then, because your battery, a normal battery can supply that much energy and so that much voltage. So basically, this semiconductor laser brought lasers to the masses in some sense, but it is also has these very unique advantages that we will start discussing deeper in the next class on Wednesday. Okay, good. So meet on Wednesday. We can stop here today.